Hello everyone, this is Srijit and welcome to MCAC 3.5 Advanced Database Management System. Today we start discussion with the distributed database systems. Unlike parallel systems in which processes are tightly coupled and constitute a single database system, a distributed database system consists of loosely coupled sites that share no physical components. Furthermore, the database systems that run on each side may have a substantial degree of mutual independence. Each side may participate in the execution of transactions that access data at one site or several sites. The main difference between centralized and distributed database system is that in centralized systems, the data reside in one single location, whereas in distributed database systems, the data reside in several locations. This distribution of data is the cause of many difficulties in transaction processing and query processing in distributed database systems. Let's see one by one. In this topic, we are going to cover the following things. We start by classifying distributed database as homogeneous or heterogeneous, then address the question of how to store data in a distributed database. Then we outline a model for transaction processing in the distributed database. Then we describe how to implement atomic transactions in the distributed database by using special commit protocols. Next, describe concurrency control in distributed databases. Next, we will outline how to provide high availability in a distributed database by exploiting replication, so the system can continue processing transactions even when there is a failure. Next, we discuss query processing in distributed databases and issues in handling heterogeneous databases. All discussions are based on a sample database with a table structure as follows. We have a table branch with branch name, branch city, assets. Then we have a table account, account number, branch name, balance. We have a depositor, customer name, account number. A distributed database system consists of loosely coupled sites that share no physical components. Database systems that run on each site are independent of each other. They may be same or different. There are transactions that access data from one site or more than one site in distributed database systems. Now let's see homogeneous and heterogeneous databases. In a homogeneous distributed database system, all sites have identical database management system software. They are aware of one another and agree to cooperate in processing users' requests. In such a system, local sites surrender a portion of their autonomy in terms of their right to change schemas or database management system software, since sites must contain identical software. That software must also cooperate with other sites in exchanging information about transactions to make transaction processing possible across multiple sites. In contrast, in a heterogeneous distributed database, different sites may use different schemas and different database management system software. The sites may not be aware of one another, and they may provide only limited facilities for cooperation in transaction processing. The differences in schemas are often a major problem for query processing, while the divergence in software becomes a hindrance for processing transactions that access multiple sites. Next, let's see distributed data storage. Consider a relation R that is to be stored in a database. There are two approaches to storing this relation in the distributed database. First one is replication, where the system maintains several identical replicas or copies of the relation and stores each replica at a different site. The alternative to replication is to store only one copy of the relation R. Then we have fragmentation. Here the system partitions the relation into several fragments and stores each fragment at a different site. Fragmentation and replication can be combined. A relation can be partitioned into several fragments and there may be several replicas of each fragment exist in the system. Data replication. A relation or fragment of a relation is replicated if it is stored redundantly in two or more sites. Full replication of a relation is the case where the relation is stored at all sites. If we have n sites, all n sites will have copies of that particular relation. Fully redundant databases are those in which every site contains a copy of the entire database. Here, n sites each contain entire database copy. There are a number of advantages and disadvantages to replication. Let's see one by one the advantages. Availability. If one of the sites containing relation R fails, then the relation R can be found in another site. Thus, the system can continue to process queries involving R despite the failure of one site. Then we have increased parallelism. In the case where the majority of access to the relation R result in only reading of the relation, then several sites can process queries involving R in parallel. The more replicas of R there are, the greater the chance that the needed data will be found in the site where the transaction is executing. Hence, data replication minimizes movement of data between sites. Then the disadvantages, we have increased overhead on update. The system must ensure that all replicas of the relation R are consistent. Otherwise, erroneous computations may result. Thus, whenever R is updated, the update must be propagated to all sites containing replicas. The result is increased overhead. For example, in a banking system where account information is replicated in varied sites, it is necessary to ensure that the balance in the particular account agrees in all sites. Controlling concurrent updates by several transactions to replicate data is more complex than in centralized systems. We can simplify the management of replicas of relation R by choosing one of them as the primary copy of R. For example, in a banking system, an account can be associated with the site in which the account has been opened. Next, let's see data fragmentation. If relation R is fragmented, R is divided into a number of fragments R1, R2, etc. to Rn. These fragments contain sufficient information to allow reconstruction of the original relation R. There are two different schemes for fragmenting a relation: horizontal fragmentation and vertical fragmentation. Horizontal fragmentation splits the relation by assigning each tuple of R to one or more fragments. Vertical fragmentation splits the relation by decomposing the scheme R of relation R. That is, the schema for relation R is split into several smaller schemas. All schemas must contain a common candidate key or a super key to ensure lossless join property. A special attribute, the tuple ID attribute, may be added to each schema to serve as a candidate key. Let's see horizontal fragmentation in detail. In horizontal fragmentation, a relation R is partitioned into a number of subsets R1, R2 to Rn. Each tuple of relation R must belong to at least one of the fragments so that the original relation can be reconstructed if needed. As an illustration, the account relation can be divided into several different fragments, each of which consists of tuples of accounts belonging to a particular branch. If the banking system has only two branches, say Hillside and Valley View, then there are two different fragments. Say account 1, which is a selection from account where branch name is equal to Hillside, and account 2, which is a selection from account where branch name is equal to Valley View. Horizontal fragmentation is usually used to keep tuples at the sites where they are used the most to minimize data transfer. In general, a horizontal fragment can be defined as a selection on the global relation R, that is, we use a predicate Pi to construct fragment Ri as Ri is equal to selection from the relation R based on the predicate Pi. We reconstruct the relation R by taking the union of all fragments, that is, R is a union of R1, R2, R3, etc. to Rn. Next, let's see vertical fragmentation. Here, in vertical fragmentation is the same as decomposition that we discussed earlier in DBMS. Vertical fragmentation of a relation R involves the definition of several subsets of the attributes R1, R2, etc. to Rn of the schema R, so that R is a union of R1, R2, R3, etc. to Rn. For each fragment, Ri of R is defined by Ri is the projection of the relation R. The fragmentation should be done in such a way that we can reconstruct relation R from the fragments by taking the natural join, or R is equal to R1 natural join R2 join R3 join etc. to Rn. One way of ensuring that the relation R can be reconstructed is to include the primary key attribute of R in each Ri. More generally, any superkey can be used. It is often convenient to add a special attribute called a tuple ID to the schema R. The tuple ID value of a tuple is a unique value that distinguishes the tuple from all other tuples. The tuple ID attribute thus serves as a candidate key for the augmented schema that is included in each Ri. To illustrate vertical fragmentation, consider a bank database with a relation deposit that stores for each deposit branch name, customer name, account number, and balance. We have a tuple ID, that is tuple underscore ID, that works as a candidate key. This relation may be fragmented into a relation deposit 1 containing branch name, customer name, and tuple ID, and another relation deposit 2 containing attributes, account number, balance, and tuple ID. These may be stored at different sites, again possibly for security reason. Next, let's see the advantages of fragmentation. In case of horizontal fragmentation, it allows parallel processing on fragments of a relation. It allows a relation to be split so that tuples are located where they are most frequently accessed. In case of vertical fragmentation, it allows tuples to be split so that each part of the tuple is stored where it is most frequently accessed. Tuple ID attribute allows efficient joining of vertical fragments and allows parallel processing on a relation. Vertical and horizontal fragmentation can be mixed. The two types of fragmentation can be applied to a single schema. For instance, the fragments obtained by horizontal fragmenting a relation can be further partitioned vertically, and fragments can also be replicated. In general, a fragment can be replicated, replicas of fragments can be fragmented further, and so on. Now let's see data transparency. The user of a distributed database system should not be required to know where the data are physically located, nor how the data can be accessed at that specified local site. This characteristics, called the data transparency, or it's the degree to which system user may remain unaware of the details of how and where the data items are stored in a distributed system. It can take several forms. First, we have fragmentation transparency. Here, users are not required to know how a relation has been fragmented. And we have replication transparency. Here, users view each data object as logically unique. The distributed system may replicate an object to increase either system performance or data availability. Users do not have to be concerned with what data objects have been replicated or where replicas have been placed. Then we have location transparency. Here, users are not required to know the physical location of the data. The distributed database system should be able to find any data as long as the data identifier is supplied by the user transaction. Now let's see some naming conventions in distributed databases. The data items such as relations, fragments, and replicas must have unique names. This property is easy to ensure in a centralized database, but in a distributed database, however, we must take care to ensure that two sites do not use the same name for distinct data items. So we have some data items naming criteria as follows. Every data item must have a system-wide unique name, and it should be possible to find the location of the data items efficiently. It should be possible to change the location of data items transparently, and each site should be able to create a new data items autonomously. Let's see centralized scheme name server. One solution to data items naming problem is to require all names to be registered in a central name server. The name server helps to ensure that the same name does not get used for different data items. We can also use the name server to locate a data item given the name of the item. This approach, however, suffers from two major disadvantages. First, the name server may become a performance bottleneck when data items are located by their names, resulting in poor performance. Second, if the name server crashes, it may not be possible for any site in the distributed system to continue to run. Thus, it satisfies criteria 1 to 3 but fails the fourth criteria. A more widely used alternative approach requires that each site prefix its own site identifier to any name that it generates. This approach ensures that no two sites generate the same name since each site has a unique identifier. Furthermore, no central control is required. This solution, however, fails to achieve location transparency since site identifiers are attached to the names. To overcome this problem, the database system can create a set of alternative names or aliases for data items. A user may thus refer to data items by simple names that are translated by the system to complete names. The mapping of aliases to the real names can be stored at each site. With aliases, the user can be unaware of the physical location of the data item. Furthermore, the user will be unaffected if the database administrator decides to move the data item from one site to another. Now let's see distributed transactions and two-phase commit protocols. Access to the various data items in a distributed system is usually accomplished through transactions, which must preserve the ACID properties, that is, atomicity, where entire transaction takes place at once or doesn't happen at all. Consistency, the database must be consistent before and after the transaction. Isolation, multiple transactions occurs independently without interference. And durability, the changes of successful transaction occurs even if the system failure occurs. So it must preserve the ACID properties in distributed transactions also. There are two types of transactions that we need to consider. The local transactions are those that access and update data in only one local database. The global transactions are those that access and update data in several local databases. Ensuring the ACID properties of the local transactions can be done as we studied before in DBMS. However, for global transactions, this task is much more complicated since several sites may be participating in execution. The failure of one of the sites or the failures of a communication link connecting these sites may result in erroneous computations. In this section, we study the system structure of a distributed database and its possible failure modes and protocols for ensuring atomic commit of global transactions. Distributed transaction system structure. Each site has its own local transaction manager whose function is to ensure the ACID properties of those transactions that execute at that site. The various transaction managers cooperate to execute global transactions. To understand how such a manager can be implemented, consider an abstract model of a transaction system in which each site contains two subsystems. First, the transaction manager. It manages the execution of those transactions or sub-transactions that access data stored in a local site. Note that each such transaction may be either a local transaction, that is a transaction that executes at only that site, or part of a global transaction, that is a transaction that executes at several sites. The transaction coordinator coordinates the execution of the various transactions, both local and global, initiated at that site. The overall system architecture is as shown in the figure, and each transaction manager is responsible for maintaining a log for recovery purpose, participating in an appropriate concurrency control scheme to coordinate the concurrent execution of the transaction executing at that site. A transaction coordinator is responsible for coordinating the execution of all the transactions initiated at that site. For each such transaction, the coordinator is responsible for starting the execution of the transaction, breaking the transaction into a number of sub-transactions, and distributing these sub-transactions to the appropriate sites for execution, coordinating the termination of the transaction, which may result in transaction being committed at all sites or aborted at all sites. Now let's see the system failure modes. a distributed system may suffer from the same types of failure that a centralized system does. For example, software errors, hardware errors, or disk crashes. There are, however, additional types of failures with which we need to deal in a distributed environment. The basic failure types are failure of a site, loss of messages, failure of a communication link, and network partition. The loss or corruption of messages is always a possibility in a distributed system. The system uses transmission control protocols such as TCP/IP to handle such errors. However, if two sites A and B are not directly connected, messages from one to the other must be routed through a sequence of communication links. If a communication link fails, messages that would have been transmitted across the link must be rerouted. In some cases, it is possible to find another route through the network so that the messages are able to reach their destination. In other cases, a failure may result in there being no connection between some pairs of sites. A system is partitioned if it has been split into two or more subsystems called partitions that lack any connection between them. Note that a subsystem may consist of a single node. Next, let's see the commit protocols. If we are to ensure atomicity, all the sites in which the transaction T executes must agree on the final outcome of the execution. T must either commit at all sites or it must abort at all sites. To ensure this property, the transaction coordinator of T must execute a commit protocol. Among the simplest and most widely used commit protocol is the two-phase commit protocol, 2PC. An alternative is the three-phase commit protocol, or 3PC, which avoids certain disadvantages of the 2PC protocol but adds to complexity and overhead. This protocol is not used in practice. The two-phase commit protocol. It assumes fail-stop model. A failed site simply stop working and do not cause any other harm, such as sending incorrect messages to other sites. Execution of the protocol is initiated by the coordinator after the last step of the transaction has been reached. The protocol involves all the local sites at which the transaction executed. Let T be a transaction initiated at site Si and let the transaction coordinator at Si be Ci. Then the phase 1 two-phase commit protocol is obtaining a decision. The coordinator asks all the participants to prepare to commit transaction Ti. The coordinator Ci adds the records prepare T to the log and forces log to stable storage. And it sends prepare T message to all sites at which T is the transaction executed. Upon receiving message, the transaction manager at site determines if it can commit the transaction. If not, it adds a record no T to the log and send abort T message to Ci. If the transaction can be committed, then adds the record ready T to the log, force all records for T to stable storage and sends ready T message to Ci. The second phase is recording the decision. T can be committed if Ci received a ready T message from all the participating sites. Otherwise, T must be aborted. Coordinator adds a decision record commit T or abort T to the log and forces records onto stable storage. Once the record stable storage, it is irrevocable, even if failures occurs. Coordinator sends a message to each participant informing it of the decision, commit or abort. The participants take appropriate action locally. That was 2PC protocol. Then let's see how the 2PC handles failures. First, the site failures. Let the site Si fails. If the coordinator Ci detects that a site has failed, it takes these actions. If the site fails before responding with a ready T message to Ci, the coordinator assumes that it responded with an abort T message. If the site fails after the coordinator has received the ready T message from the site, the coordinator executes the rest of the commit protocol in the normal fashion, ignoring the failure of the site. When site SI recovers, it examines its log to determine the fate of transactions active at the time of the failure. If the log contains commit T record, transaction had completed, nothing to be done. If the log contains abort T, then transaction had completed, nothing to be done. If it contains ready T record, site must consult CI to determine the fate of the transaction T. If the transaction T committed, redo T, then write commit T record. If T is aborted, then you will write undo T. The log contains no log records concerning T. Then it implies that the site SK failed before responding to the prepare T message from the coordinator CI. Since the failure of a particular site SK precludes the sending of such a response, coordinator CI must abort T. Then SK must execute undo T. Next, let's see what happens when the coordinator fails. If coordinator fails while the commit protocol for T is executing, then participating sites must decide on T's fate. If an active site contains a commit T record in its log, then T must be committed. If an active site contains an abort T record in its log, then T must be aborted. If some active participating site does not contain a ready T record in its log, then the failed coordinator CI cannot be decided to commit T. Can therefore abort T. However, such a site must reject any subsequent prepare T messages from the coordinator CI. If none of the above cases holds, then all active sites must have a ready T record in their logs, but no additional control records such as abort T or commit T. In this case, active sites must wait for CI to recover to find decision. And this is known as blocking problem, where active site may have to wait for failed coordinator to recover. Next is handling of failures, network partition. If the coordinator and all its participants remain in one partition, the failure has no effect on the commit protocol. If the coordinator and its participants belong to several partitions, then sites that are not in the partition containing the coordinator think that the coordinator has failed and execute the protocol to deal with the failure of the coordinator. So no harm results, but sites may still have to wait for decision from the coordinator. If the coordinator and the sites are in the same partition, as the coordinator think that the sites in the other partitions have failed and follow the usual commit protocol, again no harm results. Now let's see recovery and concurrency control in 2PC. When a failed site restarts, we can perform recovery by using, for example, the recovery algorithm studied earlier in DBMS to deal with the distributed commit protocols. The recovery procedure must treat in-doubt transactions specially. In-doubt transactions have a ready T but neither a commit T nor an abort T log record. The recovering site must determine the commit abort status of such transactions by contacting other sites. This can slow and potentially block recovery. Recovery algorithms can note log information in the log. Instead of ready T, write out ready T L, where L is the list of logs held by T when the log is written. Read logs can be omitted in this case. For every in-doubt transaction T, all the logs noted in the ready TL log record are required. After log reacquisition, transaction processing can resume. The commit or rollback of in-doubt transactions is performed concurrently with the execution of new transactions. Next, let's see the three-phase commit protocol. The three-phase commit or 3PC protocol is an extension of the two-phase commit protocol that avoids the blocking problem under certain assumptions. In particular, it is assumed that no network partition occurs and not more than k sites fail, where k is some predetermined number. Under these assumptions, the protocol avoids blocking by introducing an extra third phase where multiple sites are involved in the decision to commit. Instead of directly noting the commit decision in its persistent storage, the coordinator first ensures that at least k other sites know that it intended to commit the transaction. If the coordinator fails, the remaining sites first select a new coordinator. This new coordinator checks the status of the protocol from the remaining sites. If the coordinator had decided to commit, at least one of the other k sites that it informed will be up and will ensure that the commit decision is respected. The new coordinator restarts the third phase of the protocol if some site knew that the old coordinator intended to commit the transaction. Otherwise, the new coordinator aborts the transaction. So the assumptions are no network partitioning. At any point, at least one site must be up and at most k sites participate, as well as the coordinators can fail. So in phase 1, obtaining the preliminary decision, it's identical to 2PC phase 1, and every site is ready to commit if instructed to do so. And in phase 2 of 2PC, it's split up into two phases, phase 2 and phase 3 of 3PC, where in phase 2, coordinator makes a decision as in 2PC called the pre-commit decision and record it in multiple or at least k sites. In phase 3, coordinator sends commit or abort message to all participating sites, and under 3PC, knowledge of pre-commit decision can be used to commit despite coordinator failure. It avoids blocking problem as long as less than k sites are failed. There are drawbacks. It has higher overloads. It has the drawback that a partitioning of the network may appear to be the same as more than k sites failing, which would lead to blocking. The protocol also has to be implemented carefully to ensure that network partitioning of or more than k sites failing does not result in inconsistencies, where a transaction is committed in one partition and aborted in another. So these assumptions may not be satisfied in practice, so 3PC is not a practical solution. Let's conclude part 1 on distributed systems here, and thank you for listening. We'll continue in next class.